Made different degrees of progress yesterday. And given that Le Chatelier's principle is important, I've decided to start today's conversation with what, for many of you, may be review. Because a big portion of what you were to consider yesterday in discussion class was this equilibrium system. And the chemistry which takes place in this equilibrium system if you apply to it various treatments, each of which exert an impact, a significant effect on this equilibrium system. And in general, you will recognize that what happens in an equilibrium system, since it is the most stable thermodynamic state a reaction system can achieve, is that if you do something to upset or destroy the equilibrium, Le Chatelier's principle tells us that what will take place, if at all possible, is a reaction will occur in the system to get us back to equilibrium. It's the most stable thermodynamic state in which the system can exist. Now this happens to be an acid-base equilibrium system, the likes of which you should be familiar because I had you look at this system in Chemistry 2045 laboratory. If you look, for example, at the acid-base table, you'll see this abbreviational formula for acetic acid, namely HAC, because that's not really a true chemical formula, appearing in the acid column of the acid-base table that's on the information sheet. You also see water, anhydronium and acetate ion as formulas appearing in that table. Water in both columns, acetate ion only in the acid column, and acetate ion only in the base column, and hydronium ion only in the acid column. Now we're going to talk in far greater detail about acid-base chemistry when we get to chapter 18. But since we're talking about equilibrium, I've chosen this reaction because acid-base reactions are very important. And so let's use this acid-base equilibrium system to illustrate important points that we need to focus on from chapter 17, and also use this conversation as a springboard into chapter 18, which obviously is where we're going next, since equilibrium is chapter 17. We start with a given. This is a weak acid. And in 1 molar solution, this weak acid reacts with water to give away H+, as shown by this reaction equation. Because this reaction equation shows you that as this reaction goes left to right, this thing loses H+ to this. And when this loses H+, it becomes this. Because the property of a species which shows it to be a Bronsted acid is that it has the capacity to react by giving away H+. And the property of a species which shows it to be a Bronsted base is that it has the capacity to react by capturing H+ from whatever Bronsted-Lowry acid with which that base reacted. So this reaction is showing you, if you read it left to right, H+ exchange between the Bronsted acid, acetic acid, and the Bronsted base water. And if you read it right to left, you're also seeing that this reaction shows us H+ exchange between the Bronsted acid hydronium ion and the Bronsted base acetate ion. Now then, since we are telling you right now as a given that as written this only goes 0.4%, that means the PSI for this system is acetic acid molecules and water. These are in there, but they're not principal species. If only 0.4% in 1 liter of 1 molar of this, if only 0.4% of this converted, you got 99.6%, if we cheat with significant figures, of these remaining intact. Well, practically speaking, that means in this 1 liter of 1 molar acetic acid, you still got about a mole of this, don't you? To 1 sig fig, you have a mole, which accounts for the principal system inventory that we've reported to you. Now then, I'll appeal to your horse sense. Since, as written, this only goes 0.4%, between which acid-base pair do we find the greater tendency for H+ exchange to take place? Between acetic acid and water, the reacting acid and base for this system, or between hydronium ion and acetate ion, the product acid and base for this system? Between which acid-base pair, acetic acid, water, or hydronium ion, acetate ion, do we find the greater tendency for H+ exchange to take place? The products, right? Between hydronium ion and acetate. That's why this only goes 0.4%. Because if you turn it around in the other direction, and you start with 1 molar hydronium ion and 1 molar acetate ion, this thing is practically speaking going 100%. All of this keeps with the simple fact. Take a look now at the acid-base table. Look at your acid-base table in the information sheet. What I've just said all keeps with the simple fact that hydronium ion is a heck of a lot stronger Bronsted acid than acetic acid, both of which are considerably stronger acetic Bronsted acids than water. And acetate ion, although it's a very weak Bronsted base, is nevertheless a much stronger Bronsted base than water itself. Does the acid-base table show you this? You see the arrows in the acid-base table? Because the arrows are showing you that our acid-base table is constructed so as to list acids in order of ascending strength. As you go from the bottom of the acid column to the top of the acid column, the acids in the acid column are getting stronger. Well, I hope your horse sense then dictates to you that the bases derive from these acids. We're going to talk a lot more about this in chapter 18. So now I ask you to listen rather than try to scroll down what we've said, because indeed if you want to scroll it down, but you don't get it now, you can look at the videos. Okay? The stronger is an acid, the weaker is the base derived from that acid. Because when an acid does its thing, it loses H+, it converts to a base. The name for this base is conjugate base. Remember that from 2045 lab? Wonderful. And when a base does its thing, it converts to its corresponding acid, which is known as its conjugate acid. Remember that from 2045 lab? Language. Just so we can communicate more straightforwardly about this kind of stuff. So our base column for our acid-base table is showing you that the bases are getting stronger in order of descending strength. They get stronger in descending order. Maybe what I just said a moment ago wasn't right. They get stronger in descending order. In the base column of our acid-base table, the weakest bases are at the top, and they get progressively stronger as you go from the top of the base column to the bottom of the base column, which is where we find the strongest bases listed in our table. So back to this. You considered various effects exerted on this equilibrium by way of what you did yesterday discussion class. I want to focus on the last couple of considerations. What happens in this equilibrium system if you treat it with 1 drop of 1 molar ammonia? Now, I don't know that I remembered to tell the discussion instructors yesterday to bring to your attention the fact that the 1 molar ammonia shows as its principal system inventory ammonia and water. Here's why. When I make the ammonia solution, I'm just dissolving ammonia in water. Ammonia, as it stands by itself under normal laboratory conditions, is a gas phase compound. So this reaction right here. This reaction shows the chemistry which occurs when I make ammonia solution. Ammonia reacts with water on making the ammonia solution to make ammonium ion and hydroxide ion. This keeps with the fact that ammonia is a Bronsted base. Notice that in this reaction, ammonia snagged H plus from water. This is an H plus grabber. So this is reacting as a base. Are you seeing the formula for ammonia in our acid-base table? Look at it. Okay? It's a weak Bronsted base, but nevertheless a Bronsted base stronger than water. And when we get to chapter 18, we'll be more specific in reminding you that the way we find out right now today if a stuff is an acid, we have a new pure stuff. We don't know anything about its properties. We want to know if it's a Bronsted acid. You take it to the laboratory, you dissolve it in water. Nothing fancy about that. And then you observe a property of this resulting solution known as pH. Well, heard about that, haven't you? Because if relative to solvent and water, the pH goes down when you dissolve this stuff, which means the hydronium ion concentration went up when you dissolve this stuff. The stuff you dissolved is an acid. It reacted with water to make hydronium ion, and consequently increased the hydronium ion concentration in the resulting solution compared to the hydronium ion concentration which you find in pure water itself. Similarly, if the stuff we dissolved was not a Bronsted acid but was a Bronsted base, then we'd find on pH observation that the pH of the resulting solution is higher than that of pure water. That means this stuff reacted with water all right, but it reacted with water in this case to make hydroxide ion. That's why the pH went up. Now, interestingly enough, and this is strictly serendipity, or put it another way, Mother Nature made it this way. The ability of ammonia in 1 molar ammonia to react with water to make hydroxide ion is the same as the ability of acetic acid to react with water in 1 molar acetic acid to make hydronium ion. You notice we have told you this goes 0.4% as written in 1 molar acetic acid. This too goes 0.4% in 1 molar ammonia. How about that? That tells us the numerical value, which corresponds to the strength of acetic acid as an acid reacting with water, is equal to the numerical value for ammonia reacting as a Bronsted base in water. A whole lot more on that in chapter 18. Don't worry about that now. The key point right now is to realize that since this reaction only goes 0.4%, after which the equilibrium condition is established, the principal system inventory for 1 molar ammonia is ammonia itself, AQ, because it's now in water phase, aqueous phase, and water liquid. Okay? Ammonium ion and hydroxide ion are in there, and they're in there in measurable amounts. But they are not in there at amounts which come anywhere close to the amount of this. You understand what this word principle means? Now then, we asked you to think about what happens to this equilibrium system, acetic acid, water. Any of you own that equilibrium system? Do you own that equilibrium system? Do you own it? Or do you own a sample of it? At home, do you have any vinegar? Do you have any vinegar at home? Juice. Or at home where mom and dad reside? Do they have vinegar? Yes. Well, then you own that equilibrium system. At least a sample of it. Vinegar. Often used for making salad dressing, flavoring foods. It's a good, simple glass cleaner. You get dirty mirrors at home or dirty windows? Put some of your vinegar solution in a spritzer bottle and take a newspaper. That's what you want, is a newspaper. A sheet of newspaper, wad it up. And you got all these nice crinkly quarters of the newspaper. and you rub that on the mirror after you spritzed it with acetic acid, you'll find that mirror gets so shiny and clean, it's marvelous. You don't need to buy Windex or any of that other stuff. That'll work. Now, you may have some stuff on the mirror that the acetic acid spray won't remove, but for the most part, that'll take away finger smudges and most dusts and stains and things like that, and your mirror will become nice and shiny. Interesting, isn't it? So we're going to take this acetic acid solution, a sample of which most of you just told me you own, and we're going to treat it with ammonia. Any of you got any ammonia at home? It's commonly used cleaning material. Ammonia solution, you can buy it Publix, wherever you shop. Commonly used household cleaning agent. But I suggest strongly you don't flavor your salads with ammonia. I don't think you like that too much. Application number 1 of the ammonia solution to that equilibrium is to add 1 drop. You remember the approximate volume of a drop? Because I had you do this in 45 laboratory. It's valuable information in 46 laboratory. What's the approximate volume of a drop aqueous liquid? 0.05 milliliters. That means 20 drops liquid, aqueous liquid. 20 drops is essentially a milliliter. So if you're in 46 laboratory and you need a half a milliliter of a solution that you see on the side shelf, what's easier? Fooling around with that graduated cylinder trying to collect a half a milliliter? First having to clean the graduated cylinder and then dry it out and go through all this rigmarole? Or rinse the graduated cylinder with some of the parent solution and throw it away, which means you're probably going to throw away more than the amount you need if you only need a half a milliliter. Or get out a clean dropper, pour some of the parent solution in a clean vessel like a beaker, and collect 10 drops. Counting drops, there's your half a milliliter, just like that. Nice, straightforward, isn't it? It sure beats the hell out of this other fooling around with the graduated cylinder stuff. Look at the acid-base table. If, as a consequence of our present conversation and the information in that acid-base table, you realize that ammonia is a stronger base than water. Fair enough? You see that indicated by the position of ammonia in the base column? If ammonia is a stronger base than water, which it is, that means ammonia is a better H plus grabber than water. That means ammonia is going to grab H plus from acetic acid when you make this mix. So when I put in, we're talking about I here. When I put in my drop of ammonia, to my beaker or test tube which contains that equilibrium, here's the reaction which occurs. This is the H plus grabber. This is the H plus giver. Which means those are the products. This is reacting base, reacting acid. Product acid, product base. More on that in chapter 18. Question. How many of you remember running this reaction in 2045 laboratory? Because if you took 2045 laboratory here, you all did this. You don't remember doing that? Assignment 4? Simple conductivity measurements. We had you measure the conductivity in assignment 4 of 10th molar hydrochloric acid solution and 10th molar sodium hydroxide solution. Both of those solutions showed conductivities which are off scale. The ion concentrations were greater than the readout capacity of that little handheld conductivity meter. Now, you next were asked to observe the conductivity with that same handheld meter of 1 molar acetic acid and 1 molar ammonia. Both of those gave you on-scale readings. We talked about the reasons which underlie this our last chat. The degree or extent of ionization of acetic acid to make ions at a concentration of 1 molar is only 0.4%. Same for ammonia. So the ion concentrations in those solutions are pretty daggone small. A lot greater than that for pure water. But a heck of a lot smaller than that for the 10th molar HCl solution or the 10th molar sodium hydroxide solution. And then we asked you to take the ammonia solution and mix it up with the acetic acid solution and reobserve conductivity. Anybody remember doing that? What kind of conductivity did you get after mixing the acetic acid solution, which by itself is not a very good conductor, with the ammonia solution, which by itself is not a very good conductor? You took two solutions, neither of which is a very good conductor, and you put them together, and then you reobserved conductivity. What did you then find out? Conductivity was off scale. Ha ha! What did that tell you? That tell you you ran a reaction which effectively converted molecules to ions, right? Because that meter is really telling you about ion concentrations. And now the meter was off scale, which means that reaction, ammonia plus acetic acid, was quite effective in producing ions. There's the reaction equation. You did it in 45 lab. And I did that stuff on purpose in 45 lab. And if this damn university would let me run 45 lab the way I want to, each and every one of you would do that work on an individual basis. There'd be no teams. This team stuff doesn't belong. We do it strictly as a consequence of this administration enrolling more of you than we have capacity for in the teaching laboratory. And that's not fair. You know why it's not fair? Because it interferes with the educational process. And damn it, this place is here for education. And anything that this university does that interferes with education is wrong. And Bernie Machen can take me quote on that. And if he wants to argue with me, I'm ready, willing, and able. In any public forum, I'm ready, willing, and able to meet with him. I would never talk to him in a closed room, because then he's going to give me his power over me stuff. But if I get him in an open forum, I'm going to... And I mean it. This place is for education. And anything this place does that interferes with that process is wrong. Do I sound like I mean what I say? You think I'm passionate about this stuff? This stuff is wonderful. And I'll do everything in my power to help you learn it, because it's wonderful and because it's so important. Now that's enough of that sermon. Let's get back to the chemistry. Look at the acid-base table. Since we got this on the board, and we've already talked about the acid-base table, I want you to look at the acid column and see the positions of the two acids, acetic acid, the reacting acid in this reaction, and ammoniamine, the product acid. You see these two acids in the acid column? Also, take a look at the base column. You don't have to move your eye very far, your sight of vision very far, and look at ammonia in the base column compared to acetate ion in the base column. Are you doing that? Do you see that the acid-base table tells you that acetic acid is a stronger acid than ammonium ion, a better H plus giver than ammonium ion, as is ammonia a better H plus grabber than acetate ion, a stronger base than acetate ion. You see that? Now then, we're looking at a reaction then, which takes more reactive species and converts them to less reactive species. Remember what we said? Ammonia, a stronger base, therefore a more reactive base than acetate ion. Acetic acid, a stronger acid than ammonium ion, therefore a more reactive acid than ammonium ion. What do you think the extent of this reaction is? Large or small? You betcha. Wonderful. Which accounts for why this thing is very effective at producing ions, which accounts for the conductivity result you observed in laboratory when you did this.
How does that relate If it's a large extent, equilibrium.
We're going to talk about that right now. Okay? We've now recognized what happens when the acetic acid equilibrium system was treated with this. Okay? But keep in mind, we only added a drop. So we didn't kill much acetic acid, did we? All right? But on adding the drop, we killed some of the acetic acid. So the $64 question is regarding that equilibrium system. Is how does this equilibrium system behave after we did this to it to get back to equilibrium? Does this reaction occur, or does this reaction occur to get us back to equilibrium? Keep in mind that what we did was to effectively clobber acetic acid molecules, right? So are we going right to left or left to right to get us back to equilibrium? Right to left, you betcha. Because what we did to that equilibrium system was to deplete the amount of acetic acid molecules that are part of that system. So this thing is going to behave to try to rebuild that acetic acid molecule amount which we just depleted. So there's what goes. And that's what Le Chatelier's principle is trying to show you. And we just took advantage of an acid-base system, since we're going to talk about acid-base systems in detail in Chapter 18, because they're very important. So this provides us a springboard into such. Now let's look at treatment number 2. Now we're going to, let me re-expose treatment number 2. Now we're going to put in 2 liters of ammonia. You did stoichiometry in Chemistry 2045. We recognize that acetic acid inventory, the 1 molar acetic acid, is mainly acetic acid as solute, plus water. And the ammonia solution is mainly ammonia as solute, plus water. Okay so far? So now we're going to take, practically speaking, how many moles of ammonia? It is 2 liters of ammonia, 1 molar. How many moles of ammonia do we have in that system? 2 moles. And we're going to add that to a system which contains practically how many moles of acetic acid? 1 mole. So what are we going to do to all these acetic acid molecules? We're going to kill them. We're going to wipe them out chemically. Now, will we also wipe out the hydronium ion? Of course. But the main reaction is going to involve the main ingredients of the system, the principal system components. So here again is the reaction which is going to go. Okay? So now we're faced with the question from an equilibrium standpoint. After we do change number 2, and practically speaking, kill all the acetic acid molecules. And the small quantity of hydronium ions which were in there. We killed most of them too. Okay? How does the system now inventory as principal species? Because to deal with any question of this nature, as we tried to emphasize the other day, as we re-emphasize right now, as we will continue to emphasize throughout this term, it's impossible to understand the chemistry which occurs in a system if you don't know what's in the system. So our first task will always be, let's know what's in the system. And we express our knowledge of what's in the system by doing what? Writing PSI, you betcha. Goody. How does the system now show itself to inventory? What's the system PSI? PSI is now You tell me, I'll write it down. Ammonium ion. Practically speaking, how much? 1 mole. Ammonium ion, about 1 mole. What else? Ammonia. Practically speaking, about how much? About 1 mole. What else? I'm listening. Acetate ion. Practically speaking, about how much? 1 mole. What else? The main component by far is always the solvent. So we'll write the formula for the main component like this. Right? Because it's the main component. That's it. So now our job will be to write the equation for the principal equilibrium reaction which now lives in this system. Statement. Another common sense statement which will apply over and over again in chapter 18. You look at your inventory, we've got it there. Okay? And with the support of the acid-base table, you've got that in your midst. You look at your inventory and select the formula for the strongest acid if we're trying to deal with an acid-base equilibrium. There's the inventory. What's the strongest acid now? Strongest principal acid. What is it? Ammonium ion. And partnered up with the strongest base that's in our inventory. What is that stuff? There's the inventory. Tell me the strongest base in this inventory.
Acetate.
Nope. Ammonia is the strongest base in this inventory, isn't it? So guess what? Exclamation point. The main equilibrium in the system is now an equilibrium reaction which leads to no change whatsoever in system quality, quantity, or composition. None. So even though this is the main equilibrium now existing in the system, it doesn't lead us to any change in system chemistry. So we got to look one step further to identify another equilibrium, which also is alive and well in this system, which does reflect a change in system quality, quantity, and composition. What is this other equilibrium that we have to look for?
Acetate.
We have to recognize that in addition to ammonia being a principal base in this system, there is also acetate ion. That's right. Let's do this. Have you seen this reaction just a moment ago? Only in the opposite direction? Goody. So if we looked at this reaction just a moment ago and recognized that acetic acid is a much stronger acid than ammonium ion, and ammonia is a much stronger base than acetate ion, which is why if I write this reaction going this way, it's large extent. What's its extent going that way? Small. Which means the principal system inventory for this system remains as this. because this is not going to amount to making any acetic acid molecules of consequence, nor making any additional ammonia molecules of consequence, because this thing is not only small extent, as we'll learn in chapter 18, very small extent. This is a pretty detailed look at chemical equilibrium analysis, but it's the kind of stuff we're going to do extensively in chapter 18. So let's proceed. The next thing is a takeoff, which most of you, I think, probably looked at yesterday in discussion class. But all the discussion classes didn't get to this, so we'll take a moment to talk about it. A takeoff on the equilibrium system we prepared at the end of our last gathering. Where we put together toluene with a water solution containing dissolved iodine in one cylinder, and in the other cylinder we put together water with a toluene solution containing dissolved iodine, with each water system being treated with potassium iodide to up the dissolvability of I2 in the water layer, really to make it easier for you folks in the audience to see. You remember looking at a water solution saturated with iodine in Chemistry 2045 laboratory? Oh boy, you did all kinds of stuff in 45 laboratory, which leads into this gathering. You remember doing the solutions experiment? Do you remember what you got when you took a piece of iodine, a crystal of iodine, and shook it up with water? Remember that? Or you don't remember that? You see what happens when we do this stuff in teams? Not much learning takes place. It's not your fault, though. I've already identified people who are at fault. It's not you. You'll get a very pale faint. I guess paint is a hybrid of pale and faint. Okay? Pale, faint yellow color. Well, I wanted to magnify the observability of the dissolved iodine in water. That's why I had potassium iodide in there. In any case, we're going to take that system that we talked about at the tail end of last gathering and modify it somewhat. And imagine that we put together 900 milliliters of water with 100 milliliters of toluene, in which a total of 0.500 grams of I2 is dissolved. How much mass of I2 winds up in each liquid phase at equilibrium if the distribution equilibrium constant is 70.0, which means the molar concentration of I2 in toluene is 70 times greater than the molar concentration of I2 in water when this system is at equilibrium. How can we crack this puzzle? Well, again, most of you looked at this, I presume, yesterday. We'll start with some algebra. We'll use the algebra symbol as an unknown representative with which I'm sure you are most familiar, the great X. X represents the unknown. Here, X represents mass I2 in, what do you want? In the toluene layer or the water layer? Water layer, okay. If this is true, if that's the way we define X, how do we refer to algebraically the quantity of I2 dissolved in the toluene layer? 0.500 less X. If you write that down as Y, you've now created a problem you can't solve. Because if you've got two unknowns and only one equation, you've got a system you can't crack. So here's what we now have. Therefore, 0.500 grams minus X equals mass I2 in tol layer. And that's all we need to solve the puzzle. So what I'm going to do is put a stop to this conversation here and tell those of you who didn't work this to do it, because we'll start with this at our next conversation. And one more directive. Look carefully at problem 17.1. That's a challenge problem. Look carefully at that. If